seconds. Maybe 10 seconds. Okay.
Welcome to the session. Our first speaker is Ángela Capel, who will tell us about the exponential decay of mutual information for given states and
introduction for everyone, and let's go across everyone. And you can hear now? And
Can you
it's okay.
okay.
Yes, today I presented some work with in collaboration with Andreas here in the audience and the Pérez. And well, I mean, in this project, what we essentially do is to describe the correlation properties of these states of local Hamiltonians. And in particular, what we want to do is to describe how correlations decay. So for that, we are going to use three different forms of decay correlations. And before going to the different forms of decay correlations we use, I just want to introduce some applications that we are on this page. We're going to finite lattice. For each type of the lattice, we're going to find a dimension of equal space. So to provide those states, just to be the product that we were from the spaces. And we're going to consider the unknown value of the lambda, the algebra of supporting lambda. And now, every time that we consider superior, consider the natural embedding of the observable supporting A into the supporting lambda just by tensorizing with identity in the complement of A. And now, well, we're going to talk about Gibbs state of local Hamiltonians. So let me just introduce the second part. And the Hamiltonian that we're considering here is just the sum of some local terms, as I write here. And they have, the feature that they only have, or the terms that appear here only have support on regions that have diameter at most R. And all the norms of the interactions are bounded, as I write here. And well, we're going to consider the Gibbs states. So essentially, we're going to take rho super lambda to denote these Gibbs states and at temperature beta. And well, they are just defined by the equation that I write here, as usual. Okay, so before going to the whole presentation of the results that we've done in this paper, what I'm going to do is just to give like an overview of the things that we did, so that at least we have the take-home message from the beginning. And for that, I need to compare to previous results in the literature. Here is the so-called operator correlation function, which, you know, for a lattice lambda, which is split in A, B, and C, such that B shields A from Z, is just defined by the expression that I write here. So essentially, we denote by psi sub x of an observable Q with support in X this expression, like tracing out with respect to the Gibbs state in X. And then the operator correlation function is just the supremum over all the covariances, while taking the covariances of two observables, one we support in A and one we support in C. And these observables have the feature that the operator norm is just bounded by 1. And when we take this notion, what we want to do is study the decay. So essentially, we need to study some function of the distance between A and C that bounded the correlation function of this Gibbs state between A and C. And the first result that we find in the literature is not quite what we are looking for. So it goes back to the time of Araki, to the seminal paper of '69. And he proves some exponential decay, but it's not exactly what we are looking for. We will go to the details later. And what it's exactly what we are looking for is some paper that appeared in 2014, so many years later, where Clich et al. Proved that there's some exponential decay. So this function can be taken to be some exponential decay. After that, we are going to consider also another measure of correlation, which is the mutual information. This is pretty well known. And well, it's important to compare it to the operator correlation function. It's the direct comparison is given by this inequality that I write here. And again, we want to study the decay of the mutual information. And this decay is given by this inequality. Like we want to find an F prime such that this inequality holds. And before going to the previous results on this, I need to introduce the third measure of decay of correlation we are going to study here. In this case, I'm going to refer to the conditional mutual information, and you see that now I lighted the region in between, the region B, because now this matters. So the conditional mutual information takes care of the regions A, Z, and B. It's just given by this combination of von Neumann entropies. And in this case, we can also study the decay of this conditional mutual information now between A and C condition to B. And in this case, the first result that we found in the setting we are considering goes back just to 3 years ago. And it's by Gato and Brandau. And they proved for 1D systems that the decay is sub-exponential. Okay, but actually 1 year after that, together with Kuwahara, they also proved that for high temperature, for any dimension, the decay is actually exponential. So they managed to improve that. And actually, in both papers, they explain that these results can be directly translated to the mutual information case. So we have exactly the same. For 1D systems, we have sub-exponential decay for every temperature. And for high dimensions, we have exponential decay just for high temperatures. So you see, the situation now is that, well, we know that the general belief is that in 1D, there are no thermal phase transitions. So in principle, what happens at high temperature in 1D should also happen at low temperature, right? So in principle, if we have here some exponential decay, we should be able to extend it also to low temperature in 1D. And this is what we've done in this paper. So first of all, we've proven that this operator correlation function decays exponentially in 1D for every temperature. Secondly, we've done the same for the mutual information. And well, the third result that I'm also going to mention here has to do with the decay of the conditional mutual information, but doesn't directly enter into this table. So I'll go to that later. Okay, so now that we have seen more or less the overview of these results, I'm going to proceed to explain each one of them. And we'll start with the first one, the one that concerns the operator correlation function. And now I'm just going to focus on 1D systems because this is where we are working on this paper. So I recall here the definition that I introduced in the previous slide. And now I'm going to consider a notion that Brandau and Castoriano introduced in their paper of 2016, which they call exponential uniform clustering, and essentially means that for every finite lattice in general for any dimension, lambda split into A, B, C, the operator correlation function always decays exponentially with the distance between A and C. So we are going to denote it during the whole talk like this. And now the conjecture, as I said before, is that if we translate this notion directly to the 1D case, since in 1D there are no thermal phase transitions, this should imply that exponential uniform clustering should hold in 1D for every temperature. And okay, we tried to look in the literature and find if this was already proven, and there was this similar result given by Araki, which is not quite the same. So it's sort of an infinite chain version of this result, right? So what he did in his paper in '69 was essentially consider by SAC the algebra of quasi-local observables, like in the infinite chain limit. And then he considered the unique KMS state, which is essentially the equilibrium state in the infinite chain limit. And it's just constructed by the limit of all these finite chain size of i's of Q. And then what he proved was that if you assume translation invariant interactions, then you actually have exponential decay of correlations always with the distance between A and C. And in this case, I'm just calling it, a cardinality of P. Okay, so actually, this looks sort of related to what I'm mentioning here as exponential uniform clustering. But the thing is that for the exponential uniform clustering, I need finite intervals. And in principle, these two things should be related. And this is actually what we proved. So to go from the exponential uniform clustering to Araki's result is sort of easy. It's just taking limits with increasing intervals going to Z. And then we can show that this implies the result below. And what we proved here, which is a bit more subtle, is that the Araki's result actually improves that, actually implies that there is exponential uniform clustering in 1D. So the result, even if I phrase it here, assuming translation invariant interactions, what we are proving is just that this form of decay of correlations and this form of decay of correlations are equivalent. And then if you have translation invariant interactions, both of them hold. Okay, so this is the first result that I wanted to mention. The second one concerns the mutual information, as I said before. And for that, well, as I said, you can relate the mutual information between two systems A and B. with the correlator, the operator correlation function by this inequality, just by using Helder's and Pisker's inequalities. And actually, it's important to study both of them separately because, of course, decay of the mutual information implies decay of correlations, but the other way around is not always true. In particular, we know that there are examples in the context of quantum data hiding in which there are small states with small operator correlation and large mutual information. And one of the reasons of studying mutual information and the decay between separated regions is that actually when you don't consider separated regions but adjacent, you can study area loss. So essentially, if you consider now a region A containing lambda, and you want to see how the mutual information between A and its complement behaves, we say that there's an area law when an inequality such as this one holds. And this is something that is a very important topic. And actually, the first work of area loss for the mutual information goes back to 2008, but it was recently improved a couple of years ago. And this improvement is just with respect to the beta, so with respect to the inverse temperature. The paper of 2008 scaled like linearly with beta, and the improvement in 2020 scales with beta to the 2/3. And also in 2021, there was another paper in which area laws were provided for geometric range divergences, and I'm going to introduce these quantities in the next slides. So actually, thanks to Marco's tutorial, I don't have to introduce a lot. So first of all, let me just say that even though I said we are proving here a decay of the mutual information, what we are proving is actually something stronger. And for that, I need to recall the Belafkin-Stashevsky relative entropy, which is a different relative entropy that is not the omega k one, not the usual one. And geometric range divergences, which are given by the expression that I write here for every alpha greater than 1. And we know that this inequality holds between the quantities we're considering here. So between the relative entropy, it's always upper bounded by the BS entropy, and this is also upper bounded by any of the geometric range divergences because they are monotonically increasing. And actually, if you remember, we defined the mutual information from the relative entropy, so one can do essentially the same for the BS relative entropy and for the geometric range divergences. In particular, one can define the BS mutual information in this form. And what we prove here is actually that the BS mutual information is bounded by the quantity that I write here. So by multiplying a state rho in A and Z by the tensor product of its marginals between A and C inverted, and seeing how far this is from the identity. So seeing essentially how far rho AC is from being a tensor product between A and C. And well, if you put together all the inequalities that I mentioned in the previous slides, you have the chain of inequalities that I write here. And as you can imagine, what we are going to bound now is the term that I wrote here in the right-hand side. So the main result that we have in this paper is essentially that if we assume exponential uniform clustering, then we have exponential decay of correlations for this mixing condition. This is how we call this norm of seeing how far rho is from being a tensor product between A and C. And now if you put this together with the result I mentioned before for the exponential uniform clustering, relating it to Araki's result, the corollary that we obtain is actually that these three things are equivalent. So with Araki's result, we said that here 1 and 2 are equivalent. So exponential decay of correlations for the infinite chain thermal states is equivalent to exponential uniform clustering. And here we are showing that exponential uniform clustering implies exponential decay of the mutual information, and the other one is trivial. So we have that these three things are equivalent. And as I said, Araki proved that if you assume translation invariant interactions, you actually have one. So that means in particular that we have all of them. And this is the main corollary that we obtain from our result. Good, so of course I cannot present the whole proof of the result here, but I can give you an intuition on the main tools that we are using because I think it's cool, I think they're pretty useful. And the main ingredients that we are using here are, first of all, imaginary time Lieb-Robinson bounds that are also due to Araki in his paper of 69. And these Lieb-Robinson bounds essentially tell you that if you have an operator Q that has support in a small region like this, if you take like the imaginary time evolution of this operator, you can approximate it. I mean, it's something that has support everywhere, but you can approximate it with some observable that has support in a region that is nearby the support of the operator Q and decays very fast, decays super exponentially fast. And actually, using that, we can bound the Arrakis expansionals, as I write here. So they are just the product of these two exponentials that I write here. And if the Hamiltonian was commuting, this would just be the exponential of the terms of the Hamiltonian in the boundary between A and B. Since it's not commuting in general, you see that the situation is a bit more subtle, but it's something that decays very fast, as I'm writing in this picture here. And apart from that, we need to use also exponential uniform clustering. This is why we had to prove it at the beginning. And we also need to use local indistinguishability, which is also due to Brandao and Castoriano from 2019. This just essentially tells you that marginal if you consider a Gibbs state in row ABC and take its marginal in A, it's essentially almost indistinguishable to just considering a Gibbs state in A and B and taking its marginal in A. Okay, so I'm going to go very fast to the last result that we present in this paper, and it has to do with the conditional mutual information, as I said before. For the conditional mutual information, we know that there are two very important properties. One of them is strong subadditivity, and another one has to do with recoverability. So we know that the conditional mutual information vanishes if and only if row ABC is a quantum Markov chain, and in particular, it means that there is a recovery map that allows to recover the state from its marginal after tracing out A, for example. And in particular, this was used by Kato and Brandao in 2019 to prove the following result. So as I said before, they proved that in 1D, the conditional mutual information decays sub-exponentially with the bound that I write here, but they didn't only prove that. They also proved that actually there is a recovery map that allows you to reconstruct, in some sense, or almost reconstruct your state row up to a sub-exponential error with the size of B, of the middle system. And well, the main drawback of this is that this is not the PETS recovery map, which is the one we are more familiar with, but it's a very nice recovery map anyway. And what we do here is essentially something similar, but we are studying the BS entropy. So what we do is just take this picture from the relative entropy to the BS entropy, and we prove the following. So we consider, first of all, the BS conditional mutual information, which is just the analogous definition from the conditional mutual information to the BS setting. And what we proved with Andreas some years ago is that you have data processing inequality for the BS. This is something that is well established. And you have equality in the data processing inequality if and only if you can recover your state in this form. And actually, when you take the simplification to the tripartite state and sigma being a marginal of rho, then we have this expression, which is the analogous expression of quantum Markov chains in the relative entropy case. And in this case, we call it just being a BS recoverable state. And if you see, this is sort of parallel to the picture I was mentioning before for the relative entropy. So what we do here is actually, we prove that you can reconstruct a Gibbs state in ABC by its BS recovery condition. And now the price you have to pay is actually much faster than in the other case. Now it's super exponential instead of sub-exponential. So that means that, okay, this is not exactly a recovery condition because, it's in particular, it's not self-adjoint, but still it gives you a lot of information on the Gibbs state. So maybe it's a new interesting tool that one can start to use in this context. And I'm going to finish by mentioning a couple of applications that we found of these results, because we find the results interesting per se, but it's even more interesting that we have like a couple of nice applications of the main two results of the paper. The first one of them has to do with this exponential decay of the mixing condition I was mentioning, which in particular implies the exponential decay of the mutual information. And the thing is that this quantity is something that had appeared to us a couple of times before in the context of proving modified logarithmic Sobolev inequalities. So actually, in a paper in 2021 with a bunch of collaborators, what we proved was that if you assume that this condition holds, so that you have some exponential decay with the distance between two systems and you assume something else, then you have a positive modified logarithmic Sobolev inequality for the heat dynamics. So then in this case, having proven that our result holds, that we have exponential, if we have exponential uniform clustering, then we have this exponential decay. This is actually pretty useful. And actually last year, by the end of the year, like 3 months ago, we managed to extend this result to Davis generators in 1D. And this allowed us to prove that there is a positive MLSI It depends logarithmically with the system size, but still, there is a positive MLSI for Davis generator in 1D for every temperature, which is pretty cool. It was an interesting open problem. And well, this proof has two main ingredients. One of them is exactly what we have proven in this paper. And the other one is actually what Lee Gao presented in his talk the other day. So if you attended it, then you know how to prove the result of the paper in 2021. And well, just to conclude, I want to mention another application of the other result of this approximate recoverability by this BS recovery condition. And the thing is that since you see, we are writing the BS recovery condition in a certain order. So we have the system A just in one side and the system C on the other side. And this makes you think that maybe you can use it recursively, right? To construct some reconstruction of the state in many different systems by just using this result recursively. And this is what we've done in a preprint that we are going to post on arXiv in the next few weeks. And it essentially tells us that you can approximate your Gibbs state by MPOs in this form, so obtaining a bound like this. And without going into many details here, let me just say that the bound dimension one would obtain here would be of the order of log of m over log of m. And this should be compared to the previous result by Uehara, Alhambra, and Anshu, where they obtain some log of m. So the improvement on the bound dimension is not very high, but on the other hand, we have something that is analytical. So it's probably interesting for many other things. Okay, so to conclude, what we've done in this talk is to show the equivalence between these three things. We've also seen that if we assume translation invariant interactions, all of them hold, and we've applied it to a couple of interesting applications, I mean, a couple of different contexts. And now we have many open problems, but of course I prefer to hear your questions. So thank you very much for your attention.
Hey, if there are questions for Angela, please come up and ask.
Hi, Angela. Thanks for a nice talk. And I would like to ask you, do you have something that's you can conclude for conditional mutual information, as you mentioned?
Yes.
I mean, it's like, do you have some norm expression, then you can conclude the mutual information is small. Do you have the analog of a norm expression that you can conclude the conditional mutual information is small, or conditional BS mutual information is small? That's my question.
Not really. I mean, that's a very good question. We don't have it for the moment. It's very difficult to compare these two quantities.
Okay.
It would be really interesting to know that one would imply the other thing. It's a very interesting question, and we are working on it actually. But yeah, for the moment, we haven't proved something of the sort. But yeah, it's an interesting question.
Okay, thanks.
Hi, thanks for the great talk. So you say that these results hold for translation invariant Hamiltonians. I was wondering if you had any thoughts about whether or not it would also generalize to non-translation invariants?
That would be great, yeah. We don't really know. We don't really know. I mean, for the moment, we were more interested on proving the equivalence between the three things. And well, of course, we got for free that for translation invariant interactions they hold. But we don't really know if there are any other examples for which they do hold.
Okay.
But it would be interesting to know, yeah.
Yeah, we'd be interested to discuss. Thanks.
Okay, thanks.
Okay, let's thank Angela again for a really nice talk.